Now we can
Okay.
start, and we
I
started
understand.
to record.
So thank you, Joran, for this nice introduction. So the title of my talk is very long, you know, it's a closure problem for turbulence at very large Reynolds number. So I hope giving this talk at EMFL, most people understand what I mean by that, you know. And so this is a work I did with Martine Le Berre, who is, from what I understand, is attending also this webinar. And so what I'm going to do first in my presentation is try to, I've been asked to do that, I'll try to more or less summarize what I did scientifically in the past concerning turbulence, because I did other things than turbulence, but I worked also a lot on turbulence. And then I will switch to the problem of closure for turbulence at very large Reynolds number, which is in title of my talk. So please, next slide. So as I say in this work, you know, what I'm going to do, what I mean by closure is something which has a well-defined meaning. You know, it has been a problem considered long ago by Boussinesq first, how to represent in the exchange of momentum in fluid mechanics, how to represent the effect of turbulent fluctuation. And this is something which is relevant for turbulence, and it was also understood first by Boussinesq and by Prandtl and Landau and others, since that this cannot be done by considering, by simply extending the idea of fluid mechanics of viscosity. You know, you have to have some sort of viscosity to take into account the exchange of by turbulent fluctuation, but this has to be far more complex. This is then introducing a coefficient of viscosity in the equation when you go from Navier-Stokes to when you go from Euler to Navier-Stokes. So my point, and I will try to insist on that, is that because of the constraint coming from the from the structure of the equation for turbulence, in particular, if the shear viscosity is negligible, so one has to rely on something which is, in some sense, completely described by the Euler equation without viscosity, which puts a lot of constraint on the modelization of turbulence. So in particular, because of that, the equation I end up at we end up with Martine are fairly complex. They are integral equations, so they are not very easy to solve. But we managed to find a few cases where those equations of closure can be solved explicitly, almost completely. You know, they are not given by analytic equation, you know, by analytic solution, but one can at the end, you know, get a nonlinear integral differential equation which can be solved numerically, which is not too difficult to solve. So, and what is interesting is that in at least the case I will insist on, which is the case of Poiseuille, there is the flow as in a Poiseuille flow in between two plates. The turbulent flows has a fairly complex structure. There is a viscous boundary layer. There is a logarithmic layer, which is something which has been known since von-Karman and Prandtl. And there is also inside a fully turbulent domain. And so this is a kind of triple deck situation. So next slide, please. Next slide. So to come to more or less, which is not what I did on turbulence. So I started working on chaos theory, and at this time I had a strong collaboration with the group of Pierre Berger and Monique Dubois in Saclay, and we worked on the transition to turbulence in a small cell, which is described by a problem of in the behavior of ordinary differential equation, finite set of ordinary differential equation, which is a topic which has a very long history going back to actually to Newton himself, and the transition to turbulence, which are described by this kind of theory, is more or less described in our book with Pierre Berger and Christian Vidal on order in chaos. And when I come, you know, in sometimes you have a random meeting with people which are very important. When I was came to MIT to teach on turbulence, you know, I was asked by William Malthus, who passed away since, who was the head of department there, Department of Applied Math. He said, he showed to me an example of transition to chaos in parallel flows, which was this was observed for a very long time at the end of the 19th century by Reynolds. And this transition to chaos in parallel flows is very strongly intermittent. And this was a little bit explained by Reynolds, and as due to the fact that the transition is subcritical. It means that the instability tends to feed itself, you know, and doesn't reinforce the nonlinear terms, may grow the instability. This was more or less the explanation which was given by Reynolds. And by building on this idea and other things, I found a theory of, I devised a theory of this transition to turbulence in parallel flows, which is not at all related to the transition to chaos in system with finite number of dimensions. And I suggested that this type of transition belongs to the general class, which was known at the time. This was in the 1986, if I'm right, and belongs to the class of transition called by directed percolation, which is a class of transition in statistical mechanics. So, and this directed percolation, which is I would say a more or less remarkable example where you can apply directly a theory of statistical physics, with non-trivial theory of statistical physics, which is with critical exponents, etc., to an observation in flows. And this was done by Berger and by many other things. So next slide, please. So more recently, what I did was to try to understand what I was referring to before is the transition to turbulence in parallel flows, in shear flows, what is called shear flows, in pipe flows, and this kind of flow. It's something that happens. This intermittency happens when the Reynolds number, the critical Reynolds number, crosses a critical values. For instance, this has been studied a lot by people in the case of the Couette flow. In Couette flow, the critical Reynolds number is in the order of 430, and at this value of 430, you have this transition by intermittency in space and time intermittency. But now the field of turbulence is more widely understood as the field of study where the Reynolds number is very large, is very big, you know, not 400 something, but as big as possible. And as big as possible is an important point, you know, how big must be the Reynolds number. And I argue that it has to be very, very big. Because in the study we made with Martine, what we had shown is that in the case of the plane Poiseuille flow, you reach the regime of infinite Reynolds number when the logarithm of the Reynolds number is large. The logarithm, you know, which is very hard. You know, even if you have a Reynolds number of the order of 10 to the 6 or 10 to the 6 or 10 to the 7, you know, the logarithm is not that big, for a reason which is interesting. So next slide. So the equation, you know, the field of turbulence is amazing because it's not like, say, in particle physics where you don't even know what are the equations, you know, for instance, if you have general relativity, you have to relate the equation to gravity, etc., which is a very complex mathematical problem. In principle, in turbulence theory, one has a equation which have been written at the end of the 18th century by by Euler without the viscosity and by Navier-Stokes in the beginning of the 19th century. And by the way, the equation of Navier, the paper by Navier is exactly 200 years old this year. You know, it was written, it was published in 1822. So I guess you are all familiar with the equation which are written there. You know, this is the equation of Navier-Stokes. And to this equation, you have to add, this is a partial differential equation, nonlinear, because of the u grad u. And you have to add to this condition that the velocity field is incompressible. So the pressure there is a gauge function which allows to satisfy the incompressibility condition. So you have you have three equations, which was all three components of u enters into the game, but you have another equation which is that one, which is the equation of incompressibility. But you have four unknowns, which are the three components of velocity and the pressure. So next slide. So now I do something which has been done by at least in 2 dimensions for the first time by Boussinesq, and which is known as which was done later by Reynolds. This is called the Reynolds averaged equation. So you have a field, turbulent velocity field, which depends on time in a kind of random way, and you write the average of the Euler equation, and you get an equation which is for the balance of momentum on average. And in this equation, you have 4 terms. You have what I call the UI. This is sigma IHG. IHG is a flux of momentum. So it is to be multiplied by rho, but there is no rho. I take the density, the mass density as equal to 0 to 1, plus a fluctuating term, which is the effect of the fluctuation of u on the transport of momentum. So you have u prime. U prime is the deviation of u out of its average values. Here is the viscous term, and at the end you have the pressure term. So basically, if you the equation for the balance of momentum in the fluid is this equation, which is, there are three equations there, because you have one index j which is free. So this means that you have 3 equations, and you have 3 equations, and you have again another condition, another free term, which is a pressure, a free quantity, which is a pressure, which helps to satisfy the incompressibility condition. So the closure problem is how to express the tensor sigma as a function of the average velocity field, or average velocity flow. If you don't have such a relation, this set of equations is not closed, so one is not well defined, because one doesn't have a closed system with a finite number of unknown quantities, unknown function to find, because this is Reynolds stress, which is called the Reynolds stress, is in principle not given by this simple algebraic manipulation leading to this equation. So there have been, of course, very early attempt to close this set of equations. Basically, this amounts to get an expression which comes from whatever source of this part of the equation which is not known, knowing that you know the average velocity, this part of the equation, this Reynolds stress tensor, as a function of u. This was tried by Boussinesq and Prandtl Boussinesq at the end of the 19th century and Prandtl in the 1920s. And both had the idea of writing, following more or less the idea of Stokes and Navier-Stokes, of writing this Reynolds stress as a local function of the velocity field. So for that purpose, you have to introduce you cannot introduce a mean-free path. So what was done by, and I'm not going to say more on the Boussinesq-Prandtl theory, you have to introduce a length which depends on the geometry of the problem. But it is different of what I'll do. So next slide, please. So suppose you have this value. So what I call little sigma is the Reynolds stress. So this Reynolds stress is a symmetric tensor. There are six independent components a priori, but I consider as the very simple geometry of the plane Poiseuille. So the flow is in between two planes. Z is perpendicular to the plane, is between minus h/2 and plus h/2. So h is the gap between the two planes, and I assume that the velocity is so big that the flow is completely turbulent, so that I have a contribution to the transfer of momentum coming from the Reynolds stress. So there is also the shear viscosity, which is there, and there is, besides that, something which is called in English the pressure head, which is a gradient in the direction x, which is parallel to the boundaries. So the equation for the average balance of x momentum, so I'm not claiming to be original, is this equation, and this is a equation d sigma ij over di, transform becomes this quite simple equation in the case of the Poiseuille flow. So there is a simple integration, kind of obvious. So z, this can be integrated in the z direction. And so now the next step is we are back to this simple algebraic manipulation, leaves unknown the stress, Reynolds stress, which is this component of the Reynolds stress, sigma x z. So our theory, and I'm not going to spend too much time on that, but maybe it's important to, our theory is that when applied to this specific situation, is that this sigma, just because of scaling, this, if you remember, sigma is a proportional to u prime, the average value. So it has to be a quadratic function of u, of the velocity, which means that if you multiply every velocity by a constant, so this sigma is multiplied by the square of the multiplication factor. So it has to be a quadratic function of u. But it does not mean, contrary to what was assumed by Prandtl and Boussinesq, it does not mean that it has to be a local function. It can a quadratic function, a quadratic functional of a function, does not have to be just a product of those functions, their derivative. Actually, the most general expression for a quadratic functional is by an integral equation like the one I wrote here. So there are two remarkable things in this equation, which is our expression for the closure. So you have first that it is quadratic, because you see here you have an exponent alpha, here you have exponent 1 minus alpha, so the sum of the two exponents is 1. So this is something which is the combination of this term and that term is linear with respect to the absolute value of du over dz. So this du over dz is a reduction to this case of an expression where this this sigma is proportional to the absolute value of the vorticity. And this is because the turbulence itself is something which is generated by the vorticity in the flow. You know, if there is no vorticity in the flow, average vorticity, there is no turbulence. This is something which is well known, this is an idea of G.I. Taylor. So turbulence is somehow a way for the flow to amplify the vorticity. So without vorticity, there is no turbulence. So this equation, you know, is also the structure of this equation is such that there is no, because, you know, there are two derivatives there, this one and this one, because the dimension with respect to the scale to the space is 1 over z L square. You have two derivatives, this is L square, but you multiply this by z, which is 1 over L, so k, let me see, 1 over L square, k has to be of the order of magnitude of this is in one dimension, because there is only one direction, z. This k has to be of the order of magnitude. You have to have sigma, which is independent on rescaling of the length, because there is no typical length scale like the mean free path. So because of that, in this one-dimensional problem, k must be proportional to a length. There is a more general situation. Next slide. So this is a point which is maybe not that important. You know, this is not the most generally possible closure. You know, it's interesting to try to wonder what is the most general closure expression which is compatible with the invariant with respect to the dilation of length, invariance under change of scale in space and time, and invariant also geometrical invariance. And one can multiply the expression I just gave by a quantity like that one, which is a Laplacian. It's not very easy to find Laplacian of ui, Laplacian cube of u sub I divided by Laplacian square. So you see that there are 4 Laplacian there, Laplacian to the 4th, and you have also 4 Laplacian there. So which means that this quantity is invariant in change of scale in space. So it doesn't, this geometrical invariant, the coefficient of this quantity does not introduce any length scale in the problem. So it's a situation where you have what is called a module, you know, which, so, but I don't want to spend too much time on this question, which is interesting. So next slide. So here is a more general expression of the sigma of our closure. So you have the absolute value of u. So I should say now why there is the absolute value. This is an expression which is quadratic with respect to u and u. You have 2u, and there is also an absolute value. The reason for this absolute value is due to try to represent the fact that the forces generated by turbulence are irreversible. Turbulence is basically describes something which is an irreversible process. So irreversible means that if you change the velocity u into minus u, the force changes from f to minus f. So which is in principle, which is not compatible with a quantity which is quadratic with respect to the velocity, because if you had without the absolute, if you had no absolute value there, you would have something which is change sign with which doesn't change size with u. Although you require to have a force of this which is dissipative, you need to have a force that change sign where the sign of velocity is reversed. And that's why you have this modulus of the velocity there, of the vorticity there. And as I said, you know, this vorticity, modulus of the vorticity is there because the sigma has to be, the turbulence has to be, is there if there is vorticity in the flow. So in general, in 3 dimensions, which is not the case I considered before, in 3 dimensions, the kernel is just because of the constraint of scaling with respect to length, is just the Green's function of the Laplacian 1 over x minus x prime in 3 dimensions. And this Green's function, this is a Green's function with without boundary, when there is no solid boundaries. But in the problem I will consider, which is where there are 2 plates limiting the flow. So this Green's function has to be the Green's function with what is called the Dirichlet condition. So this is the Laplace Green's function with respect to the variable x, and it has to be the Green's function with a Dirichlet condition for x on the solid surface. And this is a way to impose that this sigma, you see, because sigma is proportional to kx. So if you have the Green function of x with a 0 condition, with the Dirichlet condition, this implies that the fluctuating velocity is 0 on the surface. So why? So the explanation that now to explain that I'll come to that a bit later, but the fact that there is an absolute value comes from the fact that you cannot derive this equation by this irreversibility formally from reversible equation like the Euler equation, because you need to have something irreversible, and this irreversibility comes from the non-analyticity of the solution of the equation we consider. So I'll come back to that at the end. Please, next transparency. So this is the function, the kernel, you know, which this kernel has this shape, you know, it is linear with respect to length, you know, you have 2 lengths. It is because this is in 1 dimension. And with this expression of the kernel, one can solve the equation for the transfer of momentum. Transfer of momentum with there is this sigmas x, z, etc. And so it is interesting to find the exact solution, how does it behave near the wall, which is a very classical problem in fluid mechanics, you know. And what is perhaps more interesting is that you cannot do that well with the purely local expression, like in the Boussinesq and Prandtl, but in this with this formulation, you know, one has somehow a full solution for the average velocity in the pipe. So, and as I'm going to show, you know, this full velocity also shows that the solution requires to reach the limit of large Reynolds number, you need to have a logarithm of the Reynolds number, which is large, which is not completely obvious. So next slide. So the solution of the equation I just discussed, and I'll show how does it behave near the wall as this structure. You know, because you know one can solve it completely analytically local solution. You know, even though one has and there is a parameter d which depends on the global solution. This is interesting because somehow it shows that this is not a local solution. This is a solution that depends on the fluctuation in all the geometry. You know, not things are not limited to a local parameter like the Prandtl von-Karman-Prandtl gamma. You know, it is something which is there. It is something which depends on the wall of the flow structure in the pipe. And d has the same dimension as nu. You know, it is a velocity times a length. And so this expression is something which is derived from the equation I wrote before, and it shows that the thickness of the viscous boundary layer is nu h over gamma d, which is a length, you know, and it is h over the Reynolds number, because the Reynolds number is d is a velocity, so more or less, and d divided by nu is a Reynolds number. And so there is, and also, you know, when Z is much bigger than this thickness, you know, the solution tends to a logarithmic boundary layer of von-Karman and Prandtl. And what is interesting is that besides that, there is a velocity field that depends on the velocity with like a logarithm of Z, but you have, in order to have a coherent value for U of Z, you need to add to it something which, as far as I can see, you know, is not in the textbook on fluid mechanics. You know, you have to add a large constant, which is possible because the equation one starts from is invariant, is Galilean invariant. So the solution of the equation I wrote down before is known up to a constant, you know, a constant in the direction, at least, you know, if there is no boundary, but inside there is a constant, there is a large constant, and this large constant is of the order of the logarithm of the Reynolds number. So next slide. Next slide. So maybe this more or less is another way of saying the same thing I just did, you know. Next slide. So the solution, at least in the logarithmic boundary, in the logarithmic layer, is a sum, you know, it's interesting, it is a sum of a logarithm like in the von-Karman-Prandtl theory, but to this you have to add a constant uniform which doesn't depend on Z, which is proportional to the logarithm of the inverse of the Reynolds number. So this function, you know, this contribution to the velocity field is something which is that becomes the dominant effect, because inside it becomes a dominant contribution to the solution, but only for very large value of the Reynolds number, because, you know, it depends on the logarithm of the inverse Reynolds number. So next slide. So this is a picture of the solution of the full equation without approximation for the profile, velocity profile at increasing Reynolds number or decreasing value of nu. So this is normalized, and you see that this is, if I remember, this is for a value of order 1 of the Reynolds number, and the nu there is of the order of 10 minus 4. So which means that the Reynolds number is very big. So you see, this is something one can more or less one expect, you know. Here in red, you have the moderate value, small value of the Reynolds number, which is a parabolic profile of Poiseuille. So as the Reynolds number increases, there is a boundary layer, and the solution becomes slightly flatter in the middle, you know, but it's a very slow process. And at the largest possible value of the Reynolds number we could reach, you know, this is a blue profile. There is an extremely thin boundary layer, viscous boundary layer there. And inside, you know, there is a kind of profile that is tending to a completely flat profile because of this, the last term, the logarithm of the Reynolds number tends to be dominant, but it needs to a very, very large value of the Reynolds number to have something which is numerically completely flat. This is interesting because it shows that, you know, it's not turbulence is not a simple problem. Turbulence with boundaries, you know, homogeneous turbulence without boundaries is fine, but turbulence with boundaries is a very tough problem because of this effect. So next slide, please. So here is a profile in sigma xz is the shear stress. You know, the shear stress is the color are the same. You know, the blue is the one which corresponds to the largest possible value of the Reynolds number we could reach. You know, and here is this is something which is more or less representing Poiseuille flow, and so there is in the middle there is a more or less this was known before. There is a constant slope of sigma, and there is a sharp jump of drop of the viscous pressure, of the shear of the shear stress, near the boundary, because of the compensation, because the Reynolds number, Reynolds stress and the viscous stress. So next slide, please. So this is interesting. There is in the limit where the Reynolds number is very big, you see that the friction coefficient tends somehow to zero, but it is also, as you can see, a very slow decay, because and this is represented by the friction coefficient as a function, plotted as a function of the logarithm. This is not something we discovered. This is called this coefficient is called the Chézy coefficient, and this slow decay of the friction at very large values of the Reynolds number has been reported since. This is the Moody's diagram. As far as I'm aware, there is no the explanation of this decay of logarithmic decay is not so well explained. But let me go to the next transparency. So concerning the connection with the turbulent friction in general, the case of the Poiseuille plane flow is not the most general case of plane flow, and it is special because in this case, the only friction is a skin friction, is a friction on the surface, on the two plates that limit the fluid. And this is that there is skin friction only in this flow is known, is very well known, but it doesn't solve completely the problem of the friction of turbulent friction. And this problem of turbulent friction has a very long history. It was not considered as turbulence because Newton was not aware of the existence of turbulence, but at least he gave an explanation for the friction of bodies moving fast in fluids which are at rest at infinity. The fluid is at rest. So the friction computed by Newton, not computed because he just gave it in words, in one sentence, which is amazing, because this sentence is correct. And Newton says that the friction is proportional to the square of the velocity. In Latin, it in duplicate ratio. And so next transparency. So this is more or less a figure which is there to explain the idea of Newton's relation. So Newton assumed a body which is moving in a fluid at very large, immobile in a fluid which is immobile at infinity. So the velocity u there is the velocity of the fluid relative to the body. So Newton says that the friction due to the resistance to the friction due to the resistance of the fluid is proportional to modulus of u times u times s, which is the cross section of the body, times rho, which is the mass density of the fluid, times a coefficient cx. And Newton apparently thought that Cx is equal to 0. It is equal to 1. And he did some experiment with bodies of various shapes, and he found that Cx is not 1. So it's a constant that depends on the shape of the body. And he tried to find a way of computing this shape, but I don't have time to explain how he did. He tried something quite smart, by the way. And the friction by Newton is due to a very simple fact. He assumes that in the wake of the body, you have a cylinder where the fluid coming, which is at velocity u at infinity, is at rest in the frame of reference of the body. So in some sense, you have to transfer momentum in the horizontal direction from the momentum from the body to the fluid constantly. This change of momentum, constant exchange of momentum, is equivalent to a force. So next transparency. I'll say a few more words on this Newton. So on what Newton did, the idea of Newton is somehow completely different of the one of the friction of skin friction. So this is a friction which is due to the difference of pressure, which is at the end of when you think a bit about the Newton's argument. This is basically a difference of pressure between the front part of the body and the rear of the body. So you have difference of pressure, and this difference of pressure, the pressure in the wake is less than the pressure upstream. So this pressure difference means that there is a pressure exerted on the body. And this pressure, it does not depend on the logarithm of the Reynolds number. It is proportional to this pressure difference is proportional to velocity square, and the coefficient Cx is a constant. So the things are more complicated than that for real turbulence, because for real turbulence there is always a contribution. There is a Newton friction which is proportional to the velocity square, and another one which is proportional to velocity square divided by the logarithm of the Reynolds number. So if the Reynolds number is very, very big, only the Newton friction survives. But before it does, there is the drag decays slowly as the velocity increases. The coefficient Cx, is decaying function of the Reynolds number. But it depends on the logarithm. What is more important is that this depends, at least for blood bodies, it depends on the logarithm of the Reynolds number. So next slide, please. So this kind of idea was discussed in the Prandtl's laboratory before the war, and Prandtl looked at the effect of the roughness of the small bumps on the surface, on the solid surface, on the effect of those small bumps on the skin friction. So the skin friction in principle, tends to zero as the Reynolds number tends to infinity. But at the same time, if you remember, the thickness of the viscous layer where you have this viscous friction tends also to zero, which means that the friction coefficient is changed by the fact that the surface is not perfectly smooth at the scale of the thickness of this of the surface, but it becomes sensitive to the small bumps, to the roughness of the surface. And this was verified by Prandtl and one of his students, Nikuradze, in the 1930s. And more or less, next transparency, next transparency, they observed, before. Okay. They observed that when this there is a dependence of this when the epsilon, the coefficient epsilon, because the epsilon becomes smaller and smaller, at some point it becomes of the same order of the size of the bumps on the surface. So you have a leveling of the skin friction, which is something which is observed in what is called the Moody's diagram. So next. And so somehow, it gives an expression of the velocity where you observe this exchange of this saturation of the decay of the skin friction. The velocity is of order gh to the power 1/2 in our model times the logarithm of epsilon, and epsilon now is the size of the bump. So next slide. This is something I will be a bit quick. I said at the beginning that the basic mechanism for dissipation, we believe to be correct, is by what we call Leray singular events. So a singular event in the sense of Leray is a solution of the Euler equation, which becomes singular or infinite time. This is a way of explaining what has been observed for a long time, beginning by Batchelor and Townsend, where in turbulent flows you have very strong, very intense events, intense fluctuation, which are very localized. And the idea is that they are localized because the Euler equation have solutions which become singular in a finite time at a given point. And this was an idea of Leray, a mathematician. It was published in 1934. And there has been lately a lot of progress by two groups. One is by El Gindi at Duke University in the US, and by my friend Sergio Rica in Chile. They managed to find an explicit, which is an incredible hard problem. Hard success. They managed to find explicit solution of the Euler equation that becomes singular in a finite time, which is something that was thought to be true for a long time, but they managed to find an exact thing. So those Leray events, with Martine, we looked at the very simple thing. If there are such singularity in a finite time, is it possible to discover, to put them in evidence in records of hot wires in a wind tunnel? So we did that. So next slide, please. We did that by analyzing the fluctuation of the acceleration. The fluctuation of the acceleration are in principle there are bigger fluctuation of the acceleration than there are fluctuation of the velocity. A of r is a fluctuation of the acceleration at point r, and A of 0 is at the fluctuation of the acceleration at point 0. And so what we did was to look at fluctuation of the acceleration in a long time record obtained by Yves long ago in Modane. So the idea was that if the acceleration, if the acceleration at our point, those points you have zero chance to see them, because you have a point, and if you record something at another point, you don't see the acceleration at this point. But this is not true, because those fluctuations have an effect at a finite distance, and if you get close enough to the point, this effect, it becomes bigger and bigger. And somehow, if you increase the acceleration, if you take the acceleration at a certain power, k, certain power, you become more and more sensitive to large fluctuation. and what is seen in some sense by increasing k, you dominate the large value of A, finish and by dominating the small probability of observing being close to a point. So you have a balance between two effects, and you see that by increasing k, this is called a structure function. The structure function has a very nice transition for k equal 4, approximately. You know, 2 is there, 4 is this function, but 6 you have a very sharp increase of the structure function at short distance, which is a way of saying that you are the event which is recorded is a large fluctuation. And we observe the same phenomenon with Christophe Josselin and Sergio Rica in a mathematical model with the singularities in finite time. So in some sense, this is a way which, as far as I know, have not been used to analyze the fluctuation of measured with outliers in wind tunnels. But this one is, so next slide. So there are other situations which can be, you know, besides the one of the Poiseuille flow, you know, which can be studied with this integral closure, because this integral closure, at the end of the day, you get a nonlinear integral differential equation, which is not the easiest thing to handle, but one can nevertheless do things, you know, in the case of the Poiseuille, but also in the case of the turbulent mixing layer, we did that also. And we are presently working on the turbulent jet and the turbulent wake and turbulent boundary layer. You know, in all cases, one can reduce the problem to a single integral differential equation, which can be solved explicitly. So there is one can basically, the idea is to transform the integral differential equation for the transfer of momentum into an equation, a single integral differential equation, nonlinear, with only one variable, which is in principle solvable. You know, we did solve it in Poiseuille and for the mixing layer and probably other. It's a challenge to do it, for instance, for a sphere or a cube or something like that. You know, but we hope to do that someday. So next, transparency. I thank you for your attention. Okay.
Okay, so thank you for these nice presentations. So now the floor is now open for questions. So you can either unmute your mic or ask the question in the chat.
Yeah.
Be shy.
Last question.
Can I ask a question?
Please.
Zoran, hello, Yves, this is Christos.
Yes, you can ask a question.
Can you hear me?
Yes.
Okay. Thank you, Yves. I will ask some simple questions just to better understand some things. So you have a closure for the Reynolds shear stress.
Yeah.
And you use it with the momentum balance equation in streamwise direction to obtain the mean flow profile.
Absolutely.
I remember in this closure you had an exponent alpha, you called it. The answer, the solution to your problem is independent of alpha, or did you choose alpha somehow? What is alpha?
The exponent alpha. So this is something I hadn't time to tell. You know, alpha is actually should be 0. You know, because of if it is not 0, we cannot match with the we cannot find the solution near a wall.
Okay, so alpha is set by your problem.
Alpha is erased, you know, because I use an old version, you know, but alpha is 0.
Then I was looking at your solution, which was in terms of this G you have here and H and something you call D. And later on, you had a similar profile, but it was simply, I think, the square root of GH, which must be the skin friction velocity.
Yeah.
So here you don't have, normally we expect here the mean flow to be equal to skin friction velocity times log of Z.
Yeah.
You have some. Do you have something different, or is it not different? What is this D?
Or D, this is, this is not the same analysis as in, I understand maybe your point, this is not, what is crucial is this inequality. This Z has to be much bigger than this length, which is basically the thickness of the viscous layer, but much less than H. It has to be much bigger. So D depends on what happens when Z, the distance to the wall, is of the order of the thickness of the gap between the two plates. So this is, it depends on the global solution. Because it is not because of the structure of the equation. You have the equation. You have an integral. So the solution depends everywhere of what it is elsewhere. You have something which is not local.
But you said that the number.
Logarithm, basically, maybe to say it in other, this logarithm is only correct in this range. Yes. Otherwise, but I'm interested, it is just a numerical, the solution of a numerical problem.
But I'm interested in the prefactor of the logarithm, modulus of G times H squared divided by 2 rho gamma D. Is this the same as a skin friction velocity, which we usually expect? The skin friction velocity should, I think, be square root of GH.
But D, this is a more complicated than that. This is a scaling, but D also depends on H. D is not a number. This D is.
You say here D is velocity times the length.
Yeah.
Perhaps the velocity is the skin friction velocity.
D depends on the velocity also. D. So this is scaling. Because you have to have this dimensionless quantity. So D depends on UH or UH. So in some sense, it is a self-consistent equation, if you wish. But this approximation is only correct near the wall. Again in this domain.
Yes. Okay. And one last question before I let the others ask questions. You gave the Reynolds stress only for the Reynolds shear stress. In principle, the Boussinesq eddy viscosity is defined for all the Reynolds stresses, or diagonal terms out diagonal. Can you write your closure also for the diagonal terms?
Yeah, sure. Let me, in the example I gave, but if back. Yeah, here.
This one. Okay, I see. For all of them, I see.
Yeah.
So you could obtain then an answer
symmetrical tensor, etc.
So your theory can also give a profile for the RMS velocities in the x direction in all 3 directions.
Yeah. But again, as I said at the end, it's in principle even because of the fact this is the balance of momentum is non-linear and an integral equation, so it's probably not very easy to solve in problems besides the one for instance, in the case of the mixing layer, we have a very nice the profile, is exactly what one expects. It has an angle, and we can compute, and which is something we try to find if this has been in the literature. Maybe we didn't try hard enough, but there is the mixing layer is interesting because you have a parameter, and this parameter is the velocity difference between the two flows. You have a velocity difference, and the angle of the cone, depends on this velocity difference. So you have a function which is in principle a function that should have been computed. We have not found it, and I suppose that people could do even with DNS or whatever. And we found only one thesis in Rennes, in France, where there are a few points we could find this function, but this function is known with 3 points. it's an interesting question. You know, there have been a lot of claims about this structure, you know, vertical structure, etc. But nobody measured the angle as a function of the velocity difference.
Actually, since you said it, one last question. You know, you talked about the jet, or I think you said jet or mixing layer. At the edge of this jets or mixing layers, you have this famous interface between turbulence and no turbulence. Do you expect your closure to apply all the way there?
Alors, what you do, what you say is very, 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 very important. You know, one is there are two from the literature. I expect two possibilities. You know, maybe I'm wrong. You know, either there is a free boundary, you know, separating the vertical from the non-vertical, from the potential flow, which is possible. You know. Because the equation, you know, because of the derivatives, the order of derivation, there could be a free boundary, you know, and the other possibility, which is what is realized in the mixing layer, is that and which is more or less what is implied by Landau, you know, for the mixing layer, by the way, and there is a decay, a very fast decay of the vorticity, you know, outside of the cone, you know, outside of the edge, but, you know, it doesn't tend to zero, you know, there is a, say, sharp decay, you know, but it is a power law. We even found the power law, you know, I don't remember, it decays like a power, you know, but it is something, I mean, for people doing experiment, I think it would be probably very hard to make a distinction between, but it could be, you know, it's an interesting question, you know, is it something which is, but you know, because this is average, you know, because this is an average fluctuation, you know, it can be that on average, you know, from time to time, you know, the fluctuation goes far away, you know, and they contribute just a little bit to a little average outside of the boundary. But it is not excluded that the equation have a sharp boundary solution with a natural boundary. It could be.
Thank you very much, Yves. Thank you. I will let others ask questions.
Thank you.
Myself offline.
Thank you, Christos.
Yeah. If I can find where I am.
So if others have questions, they can use their microphone or ask it in the chat.
No other question?
Don't be shy.
Maybe I would like to ask you one question about the slow decay of your skin friction when the Reynolds number is becoming larger. Well, as we know in the literature, there are some results, but I think these are not rigorous results for Blasius when you have decay of the skin friction. If I remember well, with 1 over the square root of Reynolds number, then Prandtl, he also proposed some decay of the skin friction with the Reynolds number. And you are mentioning a very slow decay of your skin friction with the Reynolds number. So you have your logarithmic factor in. And I'm wondering if this result, is it a rigorous result, or maybe you can elaborate a little bit about this to get some more information. I'm very curious to know how you obtain this.
The logarithm
yeah.
It's something which you know. So what happens is that you know, this is because of basically this is because of the logarithm of the what we call the von-Karman-Prandtl law. You know? So there is a logarithm, but the logarithm, at least in our theory, the logarithm depends on the viscosity. Okay. the argument of the logarithm depends on the viscosity. So it cannot be, this logarithm cannot be the full picture, because far from the viscous layer, you know, the viscosity becomes irrelevant.
Yeah.
Viscosity drops from the equation.
Yeah.
So there's something has to be done. But what has to be done is that this is something I said, you know, the equation we have are reasonably invariant under Galilean transformation in the x direction. So the solution of any equation is always up to an arbitrary Galilean boost somehow. Okay, and so this Galilean boost is a way of cancelling. You know, you have the logarithm z divided by something, and you have to add to this to have something which does not depend on the viscosity. You can add something depending on the viscosity, but without dependence, with respect to z, which is not permitted. You see what I mean? You have dependence. If the dependence on z depends on the viscosity, that would imply that you are solving an equation where the viscosity is relevant, but there is no way. So the only place where the viscosity can enter into the coefficients of the constant Galilean boost, which is arbitrary. Wow.
Yeah, but well, I just read also, thank you for that, but I also read in the chat, in fact, so it directly comes from the model for the Reynolds stress, what Martine mentioned in the chat. So it is rigorous from that point of view. If you believe in your model,
it depends on what
then,
you call rigorous, you know. It depends on what you call rigorous.
Yeah, mathematically, you can compute it. So
absolutely, it
okay.
is rigorous within our model. You know,
yeah, okay, I see. And is it going to zero when Reynolds goes to infinity?
The friction doesn't tend to zero. You know, the friction, but it is. Yeah, I mean, the friction does. You have to remember this friction is proportional to the pressure drop is assumed to be proportional to u square times this coefficient f.
Yeah.
So it is u square, but it is u square divided by log of the Reynolds number. So the friction does not tend to zero at all. You know, it just the coefficient of the u square tends to zero. But you know, the friction doesn't tend to zero.
No, I know. Yeah, sure. Yeah. Okay. Well, thank you very much.
Something which is I think which is compatible at least with this. I'm trying to remember the Moody's chart. You know, there have been a lot of. It's this kind of experiment is not easy, you know, because you have to reach a value of smoothness of the surface, which are impossible to reach. You know.
Yeah. Okay, thank you very much again.
So are there any other questions or remarks or?
Okay.
If nobody has questions, maybe I have a short questions.
Please.
In your final remark number 5, so you relate these singular Leray events to wake by stability studied by Cadot and others. Could you elaborate a little bit on this?
I don't know. I'm answering by assuming that there is some awareness of what Cadot and company did. You know, basically what Cadot did. You know, he has a spontaneous breaking. He observes after others. By the way, he observes a breaking of symmetry in the wake of what he called Hammett cars or Hammett body. So there's spontaneous breaking, and so and which is something which is quite, I would say, quite natural in our approximation, in our theory. In our theory, we have a nonlinear equation, you know, for the transfer of momentum, and this nonlinear equation, you know, it could be that because it is nonlinear and fairly complex, that for a given situation, there are more than one solution. There could be 2 or 3 solutions. There could be bifurcation in the, and this is something, the idea of bifurcation in the state of turbulence is not a new idea. You know, this was something Don Coles already had in the 1960s or 70s, if I remember. So you may have a spontaneous breaking of symmetry of solution of, as far as I'm aware, you know, Cadot is the Cadot is a new idea in this field. And so what happens is that if you have this spontaneous breaking of symmetry, what Cadot observes also is that there is a restoring of the symmetry on average. There are transitions from one symmetry state to the other symmetric state in the long term, you know. And this is because of the occurrence of very large fluctuations, and which is basically the time scale for the switching is about 100, if I remember, 1,000 times the typical time scale of the for the wake, which is h/u. And so my guess is that those large fluctuations, you know, that make the flow commute from one state to the other are Leray singular events, you know, which are with the vorticity and all sorts of things, you know, which are big scale. You know, usually they are kind of small scale, but some from time to time when there is a big fluctuation like the one described by Leray equation, you know, you have this switching from one side to the other. Maybe, you know, because they are so rare that it's not very easy, apparently, from what I understand, you know, to make more precise statement on them, you know, very rare event. But this is an interesting observation.
Yes, thank you. Are there any other questions or remarks or?
Okay.
If not, well, I will thank you for this nice presentation, and I will end this webinar for today.
Okay. So thank you. It was a very good opportunity to present my work. So I thank you for your attention again.
Yeah.
Goodbye.
Goodbye to all.
For your help, you, John.
You're welcome.
For your help.
Okay. And good evening, everyone.
Bye.